control the future.
You can't have knowledge of it.
We can't have knowledge of it, so we can predict. We can try to predict the future. See, I'm losing it. So suppose I've done my thesis, I've done my postdoc. I'm getting into a new job 5 years from now. What do you think will be the important problems? And we're going to take this further out, 20 years, which is a number Gerhard came up with, I have to admit.
20 years.
20 years from now, what do you think will be the important topics? I'll start it here.
20 years. I'll start with something shorter.
5 years and 20 years.
5 years, I think many of the topics you're seeing now will still be here 5 years from now. I don't think it'll change that quickly, partially because a lot of the interest has shifted a little bit more to networking topics, and that's a hard problem, and I don't think we're close to solving that in any which way. There are many, many open problems in that area, so that'll be around for a while. I alluded to a couple of things. Part of the reason I was interested in that I'm interested in them now is because I think they do have a future. One of those was optical communications. So that's something shorter term. Well, maybe not. The optical channel, I've been working with some people at Bell Labs, so good physicists, and they're starting to get into bandwidth problems with the fiber. So it used to be you used the fiber very inefficiently, so bandwidth wasn't really an issue. Now it is. So people are starting to do higher order modulations for optical transmission. The optical channel is, though, quite a bit more sophisticated and complicated than wireless channels. It's not nonlinear. The nonlinears are pretty complicated effects. You have this thing called the nonlinear Schrödinger equation, which you have to look at, which isn't very well understood today. The experts are people who do tons of simulations with this equation. So they just do a whole variety of simulations and then try to predict something out of that. That's definitely coming. That sort of older, in quotation marks, communication techniques are being applied to fiber optic communications. And that, in saying that, I'm also saying something a little bit related to what we talked about before. It's applications oriented. It's something where you're making a difference in something practical. In some ways it may sound like it's something, there's an old technique, all this old modulation methods are being applied to a new medium. I think I understand the old modulation methods. But what's really exciting about doing this kind of work is that you really can make a difference and an impact onto, let's say, a company. And that can make a difference for a lot of people who you're working with. And even little ideas can have make a huge difference. In terms of longer term, I mentioned networks. I also think quantum computation and communication will become more important. I don't know when that will happen. Maybe that's why I pulled 20 years out of the hat. It's far enough away that I can be totally off in my prediction. You won't be able to tell. No one will remember 20 years from now. So that's, I think, though, an area that has a long-term future. And once things become more practical and we can actually build many of these things, there'll be a lot of exciting developments around that area. I think it needs a lot of simplification, though. Making things simpler so that you can actually start understanding things from an engineering perspective rather than from a pure mathematical perspective.
So, I roughly agree. I think most of the things that are here now are still going to be around 5 years from now. At least that was certainly my hope. I think that networking is one of those areas that changes so rapidly. And one of the reasons it changes rapidly and why I think we're going to have relevance there for a long time is that it really is not just sort of a thing by itself. It interfaces with how we live. And it changes how we live. And we, by living different ways, change it. And so I think that there's going to be a lot of evolution in that direction. And, some of the things that we take for granted, like 802.11 now, we just did not take for granted not that many years ago, right? And I don't think that's going to change for a while. I think there's going to be very interesting problems that will keep emerging and where we can have a really positive role to fill. And particularly issues, for instance, like security, I think that those things in networking, even if someone said, well, okay, never mind information theory and capacity, I've solved it, I have all the throughput I want, actually getting that through reliably when some of the people in the network are not playing ball, that I don't think it's going to go away for a long time. In terms of things further out, it's so hard to predict. A lot of people are interested in biology, and I agree. I think I would say more like bioengineering. Again, if you think of yourself as an engineer rather than a scientist, my idea is a scientist tries to describe what exists. An engineer says, "Okay, I've got what I've got. What can I do with it? Let me use it as tinker toys." So if you think of yourself, I think more as an engineer, then I think certain aspects of bioengineering. People already use, in effect, approaches which come straight out of circuits into making biological circuits, right? And you can now get them off the shelf, almost as you would use to get, say, a resistor and capacitor and whatever. And so I think that we'll be able to do very, very interesting things there for a long time to come.
I guess I already alluded to some of the points in my last answer to this question. I personally, my feeling is that I think information theory historically, 50, 60 years, have been really successful in impacting engineering. But its impact has been on a relatively narrow range of problems in terms of how to build better modems, essentially, how to communicate more efficiently. But information as a topic is very broad. And I think I would like information theorists to broaden out, and think about more wider range of problems. And I think it's healthy as a community to have a set of long-standing problems we work on. At the same time, to try to diversify and look at other domains and see where our ideas, or not a hammer, but perhaps our general thinking about models and so forth, can be applied. So information is out there. There's so much information, but the only problem may not be to communicate it efficiently, but to find things, to organize things. A company like Google, essentially the goal, there was only one line, was to organize all the information in the world. It's about information. Why can't we as information theorists say something about those problems? I think as a community we should try harder, and I think there are something good for us there.
Well, I would probably agree with Gerhard that I don't think 5 years from now the frontier will look terribly different from how it does, but 20 years is a long time, so let me try to take a shot at addressing that. By that time there should be some readily detectable differences. One of these, I think, already coming to light is energy awareness. I mentioned it in my talks today because I think it's key to the way in which the biological systems work, but it's also, of course, with the mobile revolution in communications and handheld computing devices, and even with the energy dissipation problems on these high-powered chips becoming a concern for people who work on the cognate disciplines right now, where those earlier been possible to plug something in the wall and not worry about where the energy came from. Now you find yourself almost like a living system, having this battery that runs down, it's limited, and you need to design everything that's associated with it in a way that not only handles the information and control and whatever other applications computing are at hand, but also is very aware of the energy that it uses, does that smartly. So that problem is one that is not limited to the biology that I was talking about this morning. It needs to be looked at. Gerhard also mentioned the quantum communications information computing problem. I had a grant for a while, part of a subcontract with a huge effort in that the Army sponsored, and quantum, well, I think they called it quantum information, but it had a quantum communication part, a quantum cryptography part, a quantum computing part, which is what it was really mainly about, I think. And so I got exposed to more than that than I could possibly understand. In fact, at the beginning I understood none of it, but after a while I understood a little bit. I was lucky to have a great graduate student who had switched over to information theory after 3, what for him were painful years working on low temperature quantum Hall effect in semiconductors, and he understood the physics as well as pretty soon the information theory. But I do think it's a long way off. It's definitely not a 5-year way. That's 20 years away. I went to something recently where I see some improvements in the way it was some 5 years ago when that contract ended. At the end of the contract, we had a big contractors meeting, and it was held in the lab, and it was held at Harvard in the lab of Charlie Marcus, who had gone during the course of the contract from Stanford to Harvard to relocate his business. And he had a lot of room there on the bottom floor of a laboratory. It was almost as long as, half as wide and almost as long as this room, and it was all full of Charlie Marcus materials. And he toured all of us around at the end, and he showed us these big water filters and powerful machines and things, and he said, well, you know, and that's it, that's the lab. And then, so I asked him, well, where are the qubits? And he said, oh, he pointed to this little toaster oven sized thing over. He said, well, they come out over here. And I said, well, what was all that other stuff that you showed us then? He says, well, it doesn't work without that. You know, so basically, it's in a much, if it's ever going to come to fruition, it's a very long way to go. It's in a much worse state than computers were when you used to have a room about the size of the front of this thing here, all full of hot tubes trying to compute at a small fraction of what you probably have the order of computing that a handheld computer can do today, let alone a desktop or something. So that was much further along than this is in some sense to generate a qubit in any way other than optical. It's bad enough that you can kind of do on an optical bench, but to do it in the semiconductor dots or something seems to require all kinds of things that are running close to absolute zero and total vacuum with huge power inefficiencies and so forth. So, but if that does come to pass, of course, it's mathematically rather beautiful, the quantum information, more challenging than the regular information, I think. And, I just would like to add at the end, or near the end, I don't know quite when the end is, that there's another great thing about information theory, and it's the international information theory research community, which I think is just really marvelous. The people that are in this community, and it's been this way all the way from the very beginning, that you get the opportunity to work with and to and socialize with and try to get some appreciation for their minds. I think it's very special. I don't think there are many others like it, and it's a wonderful thing to become a part of if you can fit it in your life.
Okay, so with that, any last words that you would like to add about our community, our upcoming generation, some of which are here, and that'll be our closing words because we're right on time.
We don't let the students to ask this question?
Maybe after a quick round.
I don't know. I think I'll echo. I think Muriel said, keep a positive attitude. That's by far the most important thing. I think that's when things are down, try to keep a positive attitude. It sounds simple, but it makes a big difference. So, and because there's a lot of things offered to you by your institutions where you are. There's a lot of things offered to you by your people who are sitting around you, and you know, interact with them and be optimistic. Someone I know, a wise person once said, never pays to be pessimistic, and I think that's true, so stay optimistic.
Thank you. I just want to add a counterpoint to that. Sometimes it can go too far. My husband has called me a pathological optimist. So, but I think, I think again, you know, you're all extremely fortunate. We are all extremely fortunate. We get to work on these fascinating problems with amazing people in a very collegial, very special setting. And I look forward to having all of you as colleagues down the road.
Do you get the last part?
I think parting words. I think we talk about many good things about information theory. I think one thing good about the field is that the problems are clear. Problems are in general clear, and if you solve one of them, then I think that's a good thing because that gives you confidence, and confidence is a very important thing. That's one thing I learned over the years. It's really hard to be a good advisor, but one thing that I would want to be able to do as an advisor is to give confidence to the students. Because with confidence, it doesn't really matter what you do, what exactly you do in the future. Whatever you do, it will be useful with that confidence.
Well, if you have some kind of thorny advisor who's thorny in the sense that she doesn't think that you're done yet when you do think that you're done, then the way to perhaps handle this is you use the Feinstein, Emil Feinstein technique, at least what was reputed to have been the Feinstein thing that he did in the 60s. He came to, I guess it was Fano, and after Fano and Shannon had been lecturing on the problem of trying to determine not just that the error rate could be made to go to zero at rates below the capacity, but that in fact it could be made to do so exponentially fast, and nobody had proved that fact, although it was widely suspected that it was true. So Feinstein came into Fano's office, they say, I was not present of course, and he said, well, if somebody could prove that fact, would that be enough in itself to constitute a PhD thesis? Whereupon Fano said it certainly would, and Feinstein said, here it is.
With that,
Feinstein technique.
Feinstein technique. Okay, we thank our panelists very much and also our instructors for making the school a success. I'm going to officially declare it a success now. And we thank you very much.
And our organizers.